Now today we talk about the inverse. The inverse of a 2 by 2 matrix. Alright, the inverse of a 2 by 2 matrix. Alright, so before we go there, we have to back up a little bit. Alright, now we have 4 times 1/4. 4 times 1/4 is 1. Okay, we have 7 times 1/7, which is 1. Okay, now we can come down a little further. We've got 2/3, and you have to wonder what times 2/3 can give you 1. 2/3 times 3/2 give you 1. We could do one more. We could say 5/9. When we find the reciprocal of 5/9, the multiplicative inverse, that is 9/5, 45/45, which is 1. Okay, so we've all seen this before, all right? So before we can go forward, we have to go back and really know that we have seen these type of problems before. These are inverses of each other. 4 times 1/4, they're inverses, all right? We talked about reciprocals. You've heard that word before. 7 times 1/7, they're inverses, all right? 2/3 times 3/2 equals 1. Those are inverses, and also 5/9 times 9/5. Now, we have to move forward. That's not erasing like I like. Okay, so look, we have to move forward with that. Now, one thing that all those problems had in common, the answer ended up being 1. So now, y'all, let's talk about this. Let's talk about the inverse of a matrix. The definition. The inverse of a matrix now be careful of a matrix, of a matrix A. Denoted A inverse. I want to underline that because this is something that we'll see all the time. Denoted A inverse A, the original matrix, times its own inverse is equal to I. Please underline that I. It is very important. It is called, I'm writing it in blue, the identity matrix. The identity matrix. I don't have as much room in the larger board as I need, but we still make it happen. All right, A times A inverse is equal to the identity matrix. Now, the reason why I put those first problems on there, those first examples, was because we multiplied 4 times 1/4, and that took us back to what? 1. We multiplied, I think it was 2/3 times 3/2, 3/2. That answer was what? 1. All right, so now, in this particular, with these particular problems, the I, which is the identity matrix, be sure on the notes to put that in there. The I kind of takes the place of that 1. It plays the same role as that 1. Now, let me tell you why we do that, why it plays the same role. Now, one of the first things we learn in mathematics, one of the very first things we learn in mathematics is that you can multiply any number times 1 and get that original number. It doesn't matter. 3 times 1 is 3. 7 times 1 is 7. 1,500 times 1 is still equal to 1,500. That's something. It's one of the very first things that we learn. Now, let's go back to that identity matrix. For a 2 by 2, and we know we've already talked about this, a 2 by 2 is 2 rows and 2 columns. A 2 by 2 identity matrix, I want you to write it like that, is 1, 0, 0, 1. Let me write that a little bit larger. 1, 0, 0, 1. It's called the identity matrix. Now think about the identity as we talk about it in a real life sense. If a person has an identity, that's who they are. They remain the same no matter what. When we talk about the identity matrix, we talk about a matrix is going to allow the other matrix to stay the same. Now, let me give an example right here. Now, we're kind of going the long way, but you'll see why we do it this way in 1 second. Now, just say I have 5, 2, 4, 3. I have a random matrix A. And I multiply it by the identity matrix. 1, 0, 0, 1. Let me put it up on there. Now remember, I'm going to say this and I'm going to stress it. The identity matrix plays the role of your 1 when we're talking about real numbers. So now, remember how we had to multiply the rows and columns. First row, first column, first row, second column. Second row, first column, second row, second column. This is basically dot products, all right? So yeah, we have 5 times 1 plus 2 times 0. Remember, 5 times 1 is 5 plus 0, which was 5, okay? First row, second column. We had 5 times 0 plus 2 times 1. 0 plus 2. That gave us 2. All right. We had 4 times 1 and 3 times 0. Second row, first column. 4 times 1 is 4 plus 0. That was 4. And now we have 4 times 0 plus 3 times 1. That's 0 plus 3, which gives us 3. All right. So now this is what we mean. The same way we said 5 times 1 is equal to 5, or 9 times 1 would be equal to 9. The matrix times the identity matrix would still give us that original matrix A. It doesn't matter what matrix we put in, it's going to hold true because that is the identity matrix. Very, very, very important. All right. Now let me write a little bit larger. It doesn't matter. I picked a random matrix right there. It does not matter. Let's pick another one. 3, 8, 5, -2, 1, 0, 0, 1, the identity matrix. Okay, we go through everything. 3 times 1 plus 8 times 0, 3. 3 times 0 plus 8 times 1, 8. You're going to have to refer back to the notes. 5 times 1, -2 times 0, 5. And then 5 times 0 and -2 times 1. That would give us a -2. So now we see it again. We had that matrix A, which we just made up. A times I would still give us that A. The identity matrix maintains everything. Now, we said all of that to say this. You have to maintain it. Remember, the inverse is the matrix to where we can multiply A times, we have to find the inverse to get the identity, all right, to get the identity matrix. So now, we're going to talk about this for a second. I'm going to give you a formula for it. Now, there are multiple ways to do a 2 by 2. I'm going to show you this way. It's a little bit simpler and less time consuming. We will learn other ways, of course. You need to know as many ways as we possibly can, because sometimes you may get to a point where this way may not be working or may be a little bit tougher. So we need to be able to move to our other method. All right. So now I'm going to give us a random matrix, y'all. Let's say 2, 3, 1, 4. Now, the first thing we need to know each time we get ready to find the inverse. 2 times 4 is 8 minus 3, which gives us 5. I'm underlining that. This is called the determinant. Yeah, the determinant is one of the most important topics. When you get to linear algebra, the determinant has a whole chapter to its own, but the determinant is going to help us in a lot of ways. So the determinant is 8 minus 3, which is equal to 5. That's the main diagonal minus the minor diagonal. 8 minus 3 is equal to 5. All right. So now, this is what we have to do. You have that 5 down on your notes. So now, this is what we need to do. And this is how we find the determinant. Yeah, just say we have A, B, C, D. The determinant is given. This is what we do. And I should have, I'm trying to write bigger. I apologize. We go 1 over the determinant. 1 over the determinant. And then we switch the entries on our main diagonal. And we negate the entries on our minor diagonal. I say the other diagonal. The remaining problems. That's a little bit better. So 1 over AD minus BC. D, A, we switch those, and then negative C, negative B. We negate those. Now, a lot of different ways we can use the inverse, y'all. A lot of different ways, but we won't go into it too much right here. You will have it in the notes, so we'll check. So now, y'all, let's back up. Sometimes it's easier for students to do it with the numbers, but I still have to show a good formula just for reference. All right. So y'all, let's go back. Let's say A is equal to 2, 3, 1, and 4. 2, 3, 1, 4. Now, our determinant. Remember, that's 1, 8 minus 3, which was 5. We've got the 5, 8 minus 3. Okay? And now, remember what we had to do in the previous case. We had to switch the numbers on the main diagonal. So that was what? 4, 2. Okay? And then we needed to negate the minor numbers. That's negative 3 and negative 1. All right? We have to go back and review the notes on scalar multiplication. Yeah, this is all we do. 1/5 times 4. 1/5 times 4 is equal to 4/5. 1/5 times negative 3 is equal to negative 3/5. 1/5 times negative 1 is negative 1/5. And then 1/5 times 2 is 2/5. That's our inverse. Now, this is how I want you to check your answer. Remember what we said at first. When you multiply the matrix, the original matrix A, sorry right there, times the inverse, it should get you back to the identity matrix 1, 0, 0, 1. I went around the world with it, but I did it on purpose. I wanted to do it just to show you the relationship with this and something we've already been doing. So once again, it's 1 over the determinant. 1 over 4 times 2, 8 minus 3. Y'all had to save space right here, right? 8 minus 3. That's what gave us the 5. Switch the entries on the main diagonal, and then negate the remaining entry scalar multiplication. So it is using something that we've already covered before. Okay? Okay, y'all, let's do another one. Let's say, I'm going to leave my matrices, I'm going to leave my boxes up here, the outline. Okay, y'all, this is example 2. Let's just name this one G. Alright, let's name this one G. Alright, let's say we have 6, 4, 2, and 1. Alright. Y'all, if we want to start the process, I'm like I said, the board is small, we'll fix that, but we want to start this process. Remember, 1 over the determinant. The determinant is 6 times 1 minus 4 times 2. That's 6 minus 8, which is -2. Okay? We go back through the process. Remember, no matter what, y'all, we're going to have to stay disciplined. It doesn't matter if we put 23,000 up here. We're going to stay with our process. We're not going to change. We're going to stay disciplined. And we're going to dictate to the problem. All right? Now, G inverse. Let's finalize it. -1/2 times 1 is -1/2. -1/2 times -4. Half of 4, of course, is 2. Negative times negative is positive. -1/2 times -2 is 1. And then -1/2 times 6 gives us a -3. This is the inverse. If you multiply G, the original matrix, times G inverse, okay, it will get you back to the identity matrix, 1, 0, 0, 1. What you basically have done is multiplied 5 times 1/5, all right, to get back. And now let's do one, well, I want to do 2 more. All right, let's say this one is D. All right, we've got this one. All right, just say this one is D. All right, now we have 3, 4, 5, and -1. Okay, this is going to give us some different numbers, all right? Remember, that's 1 over the determinant. The determinant here is 12. 3 times 4 is 12 minus a -5. 12 minus a -5. Negative and negative is positive, all right? So that's 1/17. Now we have 4 and 3 because we switched those terms. Now we have to negate. The opposite of -1 is +1, and the opposite of 5 is -5. Remember, we negate those other entries. Okay. Now we go back through it. Nothing changes. 1/17 times 4 is 4/17. 1/17 times 1 is 1/17. 1/17 times -5 is -5/17, and 1/17 times 3 is 3/17. That's our inverse. Now this is just the first way to do it. The other ways, I hate to say which one is more difficult because that all depends on the, who's doing it, but This is the most straightforward way that I have through so many years of teaching. All right, y'all, now I want us to look at one more example. Let's just call this one P. Let's call this one P. Okay. So now I'm going to put in 6, 2, 3, and 4. All right. Now the first thing, matter of fact, y'all, let's put a star by this one. This is something that we have to really watch. All right. 6 times 2 is 12. We have to find the determinant, one of the determinant. 6 times 2 is 12 minus 12, which is 0. I'm putting that star by here. Y'all, the determinant is 0. Now, what's one thing that you learned a long time ago? You can never have what? A 0 in the denominator. We can never have a 0 in the denominator, all right? It was called undefined, remember? So now, let's put right here. We cannot have a 0 in the denominator. We cannot have a 0 in the denominator. This, basically the determinant is 0, right? This is not invertible. If your determinant, if the determinant equals 0, y'all remember it was 1 over the determinant. That was the formula. If the determinant equals 0, the matrix is not invertible, meaning we cannot find an inverse. All right. So yeah, that's what we have. There are other methods. We'll look into them. You'll have work on this, but that's just a quick overview of how to find the inverse of a 2 by 2 matrix as one of our methods.